So it's with great pleasure that I have today to introduce our speaker, Charles Butch Atwood, who's from the University of Utah. Previously, he was at the University of Georgia for a number of years, I believe.
16.
16 years. But he is a native of the South, originally, from Mississippi, I believe. And he got his PhD from Florida State in radiochemistry.
Nuclear chemistry.
In nuclear chemistry. So they have a great nuclear chemistry program there. And for the last 20 years or so, he's been working on chemical education, particularly targeting large enrollment general chemistry courses. And he has been the author of several papers and several books, especially ones relating to laboratory and curriculum development for freshman classroom. Let's see, in the last few years, you've been working on developing item response theory, developing question sets and examination sets for large enrollment classes. I think, let's see, focuses on methods to improve performance in large class settings and developing the entire computerized assessment system for this state of Georgia, right?
Utah.
Or for Utah. Currently, this entire state of Utah. So today he'll be speaking to us about using this item response theory to assess and improve learning in large chemistry classes and how that relates to statewide initiatives. Thank you. Please.
Thank you very much, John. Appreciate it. And I want to thank the department for inviting me here today. I've enjoyed my stay so far. Looking forward to another good meal this evening. We ate at the Acre last night, and that was really good. As John said, I'm a native Southerner. I used to be able to say that the furthest north I'd ever lived in my life was Athens, Georgia. I broke that mold a couple of years ago. When we first moved to Utah, we got there and everybody said, well, you got to go out and you got to get snow tires, snow boots, snow this, snow that, snow thrower, snow shovel, snow. And so we dutifully went out and bought every last dadgum one of those. I spent a small fortune on snow, everything that started with snow, something else. And the first year we lived out there, it didn't snow worth beans. And, but it did snow one Saturday. And we did like good Georgians should do. We drove home as soon as it started snowing, 10 miles an hour. Everybody else flying by at 40 miles an hour. And we sat in the house and watched it snow the rest of the day. And when I got up the next morning, there was a good 6 inches of powder out there, and I thought to myself, hot damn, I get to crank up that snow thrower. This is the first time I'd ever had it done, and so I cranked that thing up, and I'm standing there with it, and I'm thinking to myself, this is the closest I'll ever come to owning a Harley. And so I got to throw snow for about an hour and a half, and that was my first experience with snow throwing. And I was the happiest snow thrower in Utah that day, I'll guarantee that. So let me talk about what we've been doing. First, a lot of this is going to be stuff that I've done at the University of Georgia, but we are now in the process of implementing it at the University of Utah. And most of the work I'm going to talk to you about today was done by Derek Bimke, who is now in a lecturer position at Bradley, and John Moody, who just completed his PhD at the University of Georgia in August and has accepted a lecturer position at Indiana State. So initially what I'm going to do is give you a very quick description of item response theory, which I did not develop, but which we have employed. How we use that in our general chemistry classes at UGA. So this is our first semester of general chemistry. This is the second semester. And then how we develop some interventions that are designed to help students based upon what we learned about item response theory. And then how Derek took and implemented cognitive load theory into the homework system that we used at UGA. And then John's work on the IRT analysis of OWL. For those of you who don't know, this is a web-based homework system that Cengage Learning has developed. And then I want to talk a little bit, can we convince you that we've improved things over time, and then show you a few things about what we're doing now at the University of Utah, and then hopefully I'll bring this to some logical conclusion. All right, so most of you are familiar with the psychometric analysis tool called classical test theory. And in classical test theory, what you do is you take an average, you take a median, you do a mode and all that kind of stuff. And that's, you probably report these things to your students after they have a test. And there's also a discrimination index that's built into classical test theory. And what classical test theory, the way it does a discrimination index, it says, here's the top 20 or 25% of the students, how they did on this question. Here's the bottom 20 or 25%, and it just takes a ratio of those two. And so if the number is, some programs put the good over the bad, and the other ones put the bad over the good. So you have to figure out whether your number is supposed to be greater than 1 or less than 1, and so forth. And it turns out that if you do classical test theory, it's really good for small samples. And so if you got a classroom of 20, this is the way to go. But if you want to do highbrow this, it's called item response theory. This is a much more modern psychometric analysis tool, and it's really good for large samples. So it has to be more than 200 for your statistics to be good. Some of the questions I'm going to show you in a little bit have been tested on over 5,000 students. So our statistics are really, really, really good. Okay? And the way it works is it tries to fit the data to this equation. And it does this by an iterative process. And so let me introduce the variables here. One, this theta is the student ability. And so you may think of that as their ability to do well on the test, or you may think of it as this kid is smart and this one's dumb. I mean, it's one way to look at it. A is the discrimination parameter, B is how difficult the parameter is, and C is the guessing parameter. So for instance, on a multiple choice question, we can get at least a ballpark figure of how many students got the right answer just by taking a shot at it. And you can buy a commercial program to do this. In our case, we've purchased Bilog MG3. And this system has been in use in other disciplines besides chemistry since basically the 1980s. But my group is one of the ones that's breaking the ground here in chemistry in terms of using it. And the way Bilog MG3 does this is we take the raw data. The raw data consists of a series of 1s, 0s, and 9s. So did the student get this question right? The answer to that is a 1. Did the student get this question wrong? That's a 0. Did the student have this question or not have this question? That's a 9. And so what we get is a whole series of 1s, 0s, and 9s for each student. And then the way I look at it, it's like an NMR data. I mean, after you get the data out of the machine, it's just a bunch of jumbled up numbers. And then you run it through a Fourier transform, and it looks like peaks. Well, this is our Fourier transform, is what Bilog MG3 is. And so the way IRT displays this is on what's known as an item characteristic curve. So I'll show you what one of those looks like. So they look like a titration curve. Best way to say it. And so what we have plotted down here is both the student ability and the question ability. So the very bright students will have a score of ability of 3 or higher, and the very poor students will have an ability of -3 or less. So right here would be sort of your average student with a 0. Then right here, the asymptote at this point right here is the difficulty of the question. And so as the questions become harder or simpler, they will move back and forth on this scale. So a simple question would be down here, have a titration curve down here on this end, and a hard question will be up here. Does that make sense to everybody? And how steep this line is, how steep this curve is the discrimination parameter. So the steeper the curve, the more discriminating it is. And then finally, this asymptote right here is the guessing parameter. So because this has an asymptote of 0.247, that tells us that about 25% of the students got the question correct by guessing. Does that make sense to everybody? Any questions about this? So what this does, the neat thing about this is that it plots both student ability and question ability on the same scale, which allows you to look at questions and say, these are the ones that will tell us whether or not you're an A student. These are the ones that will tell us whether or not you're a B student, so forth and so on. So the way we do that is by plotting.
I don't follow it. The guessing parameter that you have, is that something in which you have a 0.247 there? Is that something that you can know in advance because you've given 4 options and a multiple choice question?
No, no. What it does, the program is actually much more sophisticated than that. So what it does is it goes through and says, this student has a very low ability, but they got this question, this high ability question right. So they must, we're going to believe that they guessed at that. And it goes through and it does that for every one of those students. Now we happen to choose one that has a 25% guessing parameter, but they'll go all over the place. Okay? Does that answer your question? So the program actually does some calculations, so it's not just because you've got a 4-question multiple choice thing. In fact, most of the questions I'm going to show you were not multiple choice questions. They were numerical entries and all sorts of other things. It was designed for multiple choice questions, but that's not what we used it for. Did I answer your question, Vincent? So what we can do is plot the ability of the questions versus the percent correct. And so what you can do is say if you're going to have an A student, they're going to have 90% or higher, and that's an ability, let's say, of 1.5, just for the sake of the argument. And so you can look for questions that have abilities of 1.5 or higher and say those are A-level questions. So you go back and you do this between 80 and 90 and find those abilities, and those are your B-level questions. C-level, D-level, F-level. Does that make sense to everybody? Yeah.
So what it's basically saying is like, so you're saying that the ability is the difficulty of the question that's being given, right?
Yes. In effect, what we're measuring here is how did this question do in terms of the student ability levels.
Okay. So like, for instance, so a low ability question would be basically a recall question, like give the ideal gas law, something like that. And then something that's a higher ability is to integrate some past.
Can I show you a couple of hard questions in a few minutes?
Yes.
Yeah. Okay. There was another question I saw in the back.
I was wondering how you determine the student ability of that. Is there a diagnostic test they take?
Can you speak up just a little louder?
I was wondering how you determine student ability.
The program takes and says, okay, you did really well on the test, so you have a high ability, fundamentally, is the way it does that, okay? And the way this program works, you have to make an initial assumption. And what it's going to do is say, all right, you got a 75 on the question, you're an average student, we're going to assign you a grade of 0 on this ability scale, and then we're going to take and assign everybody an initial ability level. Then we're going to take that ability level and use that to figure out the ability levels of the questions. Then it takes and turns around and uses the ability level of the questions, and it iterates to the ability levels of the students, and it just keeps doing this back and forth, until finally it hits basically the maximum on a curve or a saddle point on a 3-dimensional plot. Did I answer your question? Okay. Now the other thing that we can plot are what are known as item information curves, and item information curves are how we determine the ability levels of the students, okay? So what this is how well do I know whether this student has an ability of effectively 1? And you can see that up here of 2 and higher, we have no information because all of the students with an ability level of 2 or higher got the question right. If you are down here, then we have no information again because all of those students got the question wrong. And in here, and it's almost like a Dirac delta function, what we're figuring out is which students and what information we have about them in terms of their ability levels. Does that make sense so far? So that's part of the answer to your question. Now the neat thing is you can take the item information curves for your test and put them together and make it what's known as a test information curve. So I'll show you a test information curve. And this is before we ever installed item response theory at the University of Georgia. And what you see is that fundamentally we were assessing at the C level, almost nothing down here at the D or A level, and almost nothing up here at the down here at the F level. And also this red curve, Raj, is the IRT equivalent of a KR21. And so what it says is that, do I know what the position, what the ability of that student is for there? And that would be, have this standard deviation fundamentally. And the other thing I want to plot is here's the information. So we were getting 6 units of information. In other words, we knew how well our students were doing up to with 6 arbitrary units of information. 1 year later, after we'd done our initial work, same test, and first thing I want to notice is that is 25, that's 20, so we improved our information ability by a factor of 3.5 in 1 year. And furthermore, we're assessing over a much broader range, and our error bars have dropped like a rock. They've gone down by a factor of 3. So knowing what our students were being assessed on improved dramatically in 1 year by doing this. All right, is everybody with me so far?
I guess I'm confused. Are these tests multiple choice tests that you're administering?
No.
So the student can get partial credit?
Yes.
Can incorporate that kind of answer in?
Yes. Okay. We built our own testing system, and so I could spend another 2 days explaining all that stuff, but fundamentally we had numerical entry questions, we had text entry questions, we had all kinds of other kinds of questions that we could do. So, but they all were done on computer. Have I answered your question?
Well, I didn't know you could type in a paragraph on a computer and get a good grade on it.
I didn't say we did paragraph. We can do like names, chemical compounds, names of chemical compounds and so forth. Okay, have I answered your question better? Okay, so one of the things that we did, for instance, was we put this question in, and so the question that we're asking the students is, what's the correct name of this compound? And so they have to type in aluminum nitrate. So that's one part of it. And the other question is, how many ions are present in 1 formula unit of aluminum nitrate? This question is among the most discriminating questions we've got in our entire data set. If I were to show this at a psychometric group, their teeth would fall out. This has a discrimination factor of 6. This is a question that fundamentally you either know or you don't know. That's how discriminating this question is. And it's at the ability level between a C student and a D student. Do we have any educators here? Yeah. Sorry, what?
All of us.
All of us are? But does your title say something education? Okay, good. Because now what I'm going to tell you, this one question right here could tell me whether or not you're going to pass or fail my class. That's how discriminating this question is. There's a first question test. First test question, what I should say. And that's how discriminating this thing is. And it also told us that there's something about this question that we need to look at. And it turns out, if you do the analysis, this isn't what they missed. That is. And if you stop and think about it, what it's trying to tell us is our students can't decode that symbol right there. Isn't that amazing? Would you like to know a common incorrect answer? 13. Why 13? 3 plus 1 is 4 times 3 is 12 plus 1 makes 13. They're counting atoms. They're counting atoms. 3 plus 1 is 4 times 3 is 12 plus 1 makes 13.
Oh, I see.
They're counting atoms. So that's one common mistake, okay? Second common mistake, 2.
Yeah, I was thinking that.
Another common mistake, 1. I don't know where in the heck that comes from. Fourth common mistake, 4 times Avogadro's number. So what this tells us is they don't understand in our notation what we mean by an ion, and they don't understand what we mean by one formula unit. And what this led us to the conclusion was that the students, what they're really struggling with is our symbolism. Understanding how we write things. Yeah?
So does this item characteristic curve measure the ability of actually naming the compound or actually...
Both. Both.
Like, how does it, I guess, incorporate both of those questions?
Because this is one question. Okay? And we've gone back and done analysis, and I can tell you it's this one they're missing. It's not that. Okay? Is everybody with me so far? Yeah. Can you speak up loudly for me?
How do you differentiate between common mistakes and guessing? Because, like, for the 13, they can be like, oh, well, I don't know this answer, but hey, there's 13, you know, let me put that. So how are you differentiating?
This was a number entry.
Right, but how are you differentiating between guessing and common mistakes?
If it's a number entry,
Right.
we're not saying that we're going to have a very small guessing parameter. In this case, it's 14%. Okay? If it's a multiple choice question, then...
You really only evaluate guessing for multiple choice.
For the most part, yes. All right? Everybody cool with this? This question is going to come back to visit us. All right? And it turns out we came to this conclusion that if we could get our students to understand the structure of ionic compounds, life would get better. And so we started working on that. And in fact, what we did was we quantified some work that Gable and Johnstone had suggested about 10 years earlier that we went and actually put a number associated with do they understand this stuff. And this turned out to be such a gatekeeper, we decided we had to do some stuff to fix this problem. Okay? So I'm going to show you another question, which is, I suspect most of you would go, no way. But let me put this up here. So the question is, we're going to ask the students to match a property with a substance, and they have a drop-down box. And on that drop-down box, they can choose HCl by itself, HF by itself, methanol by itself, or HCl and HF, or HCl, HF, and methanol. Everybody with me so far? So here's the question. Which of those substances conducts electricity well in dilute aqueous solutions? And the correct answer to that is HCl. Which of those ionizes only slightly in dilute aqueous solutions? And the answer to that is HF. Which of those can form concentrated solutions? And the correct answer to that is HCl, HF, and methanol. Which does not conduct electricity? The answer to that is methanol. And which can form dilute solutions? And again, HCl, HF, and methanol is correct. This dadgum question is so hard that only our very brightest students got it right. This is among the hardest questions we have in our entire database.
How much effort do you put into writing a question with flawless interpretation by the student, though? You're depending on flawless interpretation of the question by the student.
What we do is we will put some questions in where we're looking for misconceptions to see if we can figure out what those are, how students are having that problem, and then we go back in and we try to fix the problem. We wouldn't put a ton of these on, but there will be some. Does that answer your question? Okay. Now, why is this question so hard? Anybody want to know what parts of this question are hard?
Probably the ions again.
It's these two problems right here that are the hard ones, concentrate and dilute. Because the students believe that only strong acids can form concentrated solutions and only weak acids can form dilute solutions. And what they've done is they confused the terms strong, weak, concentrated, dilute. Okay? And that, I've had students that made an 89 on the test come in to argue with me that the correct answer to this is HCl and the correct answer to this one is HF. And so this is a case where we found a misconception, which, by the way, we worked on. I'm sorry, who was asking me that question a minute ago? We've worked on and can show that we've improved that. So one of the things we did was we took these ability levels and we plotted them versus time, effectively. So this is the first question on the first test. This is the last question on the final exam. And what we were looking for were, where were there things that were really hard for the students and where were there things that were really easy for our students? And what this allows you to do is to say, you know what, I don't have to teach this stuff very much, but I sure as heck better home in on this stuff. Now, I haven't put all of them up there, but I put quite a few so that you can see the kinds of things that the students at the University of Georgia were having trouble with. And what this allows you to do as an instructor is to know where to aim your cannon, basically. You don't have to do everything. You just got to tell enough of the story to make it make sense on this stuff and really home in on any one of these up here that you want to pay attention to. Does that make sense to everybody? So it makes you, as a teacher, it makes you more effective, more efficient, might be a better way to say it. Okay. Do you need to see anything more?
I was just shocked that percent composition and balancing equations were in your low degree of difficulty because, I mean, that's what our students have a lot of difficulty with.
Students at the University of Georgia, it was a knock a home run problem. Downright simple. And I'll show you a little bit later that that actually is a national trend. Okay? Yes?
So the y-axis says hierarchy question difficulties?
Yeah, this is the ability, and this is basically which question we did during the course of the semester.
So the ones that, like, say the add subrule for CV?
That's extremely hard.
And what about the atomic weight, like all the way down?
Extremely simple.
Okay.
Okay?
Okay.
You with me so far?
Yes.
All right, cool. All right, so after we've done our homework and we finally figured out what it is that our students don't understand, we started looking at those test questions that have the highest discrimination and ability levels. And there are several topics which we know now from this experience that give our students fits. And so we got them all fished out. And so I'm going to there are 11 of them. Let me put them all up here. If you want, you can write them all down, or if you want, I'll give John a copy of the slides. Okay? The first one is basically understanding the particulate nature of matter, which is that aluminum hydroxide problem. By the way, it doesn't have to be aluminum hydroxide. Anything that's got a parenthesis. So you can do sulfates and chlorates and so forth and so on. Nonlinear units for unit conversions, molecular shape and polarity, ionic versus covalent, strong, weak, concentrated, dilute, the other one I showed you a minute ago. Now at UGA, because we're such a theory-heavy school, we were doing a lot of physical meaning of quantum numbers. And so how do NL, ML, M sub L, and M sub S, what do they mean, and so forth, and how the quantum numbers are interrelated. Limiting reactant calculations, and it turns out just for excess reactants was the main problem. And then the last few, Lewis acids and bases, particularly the concept of electron motion, intermolecular forces, which they confuse with intramolecular forces, colligative properties, because they can't figure out how many ions there are in aluminum hydroxide. It's the same problem, back to visit again. When you do thermochemical equations, if you ask them about moles of reaction, it blows their mind. And if you do percent dissociation, it turns out that it's an algebra mistake that they make, which is based, again, on the particulate nature of matter. They don't understand that this thing's going to split up into more than one ion. And so this was it for us. So that's pretty cool. Yes, I only have to fix 11 problems, right? If I can fix these 11, then we can hopefully improve. So we headed off to ions first. It seemed like the simplest one to tackle, and it also was our gatekeeper. And so prior to the start of fall semester, we got a meeting together. We discussed all these topics, and we kept telling everybody in the faculty, you must emphasize ions, and you must have them draw. So I'll put a molecule up on the board, and I'll say, draw that, using circles, and I will walk around and see what they're drawing. And then usually I have 3 or 4 variations on a themes. I'll put those 3 or 4 variations up on the board, and then say, how many of you have this one? How many have this one? How many have this one? And then I'll say something like, okay, one of these is correct. I'm going to give you a minute and a half. You tell me which one is correct. And everybody gets to talk to one another and see if they can figure it out. And it turns out that that's fairly effective, because we gave the same question back again. And when we did that, the ability level went down. It's not as discriminating as it was. And our guessing factor went to 35%. And we believe that what happened was, instead of having the entire range of infinite numbers, we honed them into 3 or 4 smaller numbers, and that's why the guessing factor went up. Okay? Yeah.
So is the guessing factor necessarily good or bad? I guess, what is the guessing?
Well, we would prefer that they not guess the right answer, that they do it because they're intelligently choosing the right answer, or typing in the right answer. Yes. Does that answer your question?
Yeah, so I'm guessing, do you ideally want that guessing factor to become 0?
Yes.
Okay.
And I'd like for all these questions to be easy, too. That ain't going to happen. Okay? Now, based upon this work, we began to realize that we could do some really interesting stuff. So we can start to identify at-risk students prior to our first test. In fact, John, once we got good at this, we could do it after the second homework. We could tell you which students are already in trouble after the second homework. And the way we did that is we would take a homework and we would load it up with questions that are on one of these things that we know is going to give them fits. And if a student missed all of those questions, we identified them as at risk. And it turns out that was it was correct. And so what we would do is identify, after the homework is over with, we'd call out the students that were at risk. We would send them an email that passed through the hands of 3 associate deans before they would let me send it. Mine was going to say, look, you got a problem, get your ass to this meeting. It came out yay long. But basically it said the same thing. You just have to read a lot further on to get that. We could see improvements for the students who attended, but unfortunately, we could never get them to show up. I don't know why, but we just could not get them to show up. So we said, all right, plan B. So here's plan B. Turns out that if you look at human memory, it consists of both a long-term and a short-term. The long-term memory is basically infinite, so you can store as much stuff in your long-term memory as possible. But for humans, our short-term memory is somewhere between 5 and 7 bits of information. Now, what makes an expert different from a novice in cognitive load theory is that when you say the word mole to a novice, occupies about that much space. You say the word mole to an expert chemist, it occupies about that much space, but it's still 1 bit. And so we can call out all the various meanings for mole in our heads, whereas a student is only going to call out just this one very small definition of a mole. Does that make sense to everybody? And what cognitive load theory does is it attempts to find ways to maximize the transfer from short-term to long-term memory. We can further subdivide load into what's called intrinsic load. That's a result of the subject matter. Chemistry is heavy in intrinsic load. It's one of the worst subjects possible, turns out, in intrinsic load. Extraneous load, this is load that's because you didn't say things well, or you wrote a poor question or something like that. And then germane load. And germane load is what you got to figure out in order to maximize your learning. So you want to minimize extraneous and maximize germane load. And the way Derek went about doing this was he took one of our questions that's been given students fits on homework, that's rank the following in increasing conjugate base strength, and he rewrote them so that every student would be given first this question, in which we work out every step. Then we gave them the same question but with different chemical compounds, and we worked out all 2 out of the 3 steps and made them do the 3rd step. And then we did it again. We backed up another step. So they have to do the other 2 parts. And you just keep backing up and backing up and backing up. Does that make sense to everybody? Here are the topics that he chose to do. We have 4 in the first semester, 4 in the second semester. And what we did was we put in the test, we took questions that we'd done before we did this, and then we put in questions to see how they did after we had done this. And if we plot the ability level of the question before is black, after is gray, just like in the previous one, down is good. And you'll see that in 7 out of the 8, we have improved how our students are doing. They are all statistically significant. The only one where we're not is number 4. Derek went and did a 2-tailed t-test to convince ourselves that this was the case. On 7 out of 8, there was statistically significant change. By the way, I'll tell you, that is a 40% improvement right there. The other ones are around 20 to 10%. By the way, for those of you who don't know, in chemical education, 40% is almost unheard of. If you can get 5%, people go nuts. Okay? And so, only on topic 4, which was nomenclature, could we not get any change. Good old nomenclature. Okay? It's the only one we couldn't get a buy-in for. So next thing we decided to do was, with my other last graduate student at UGA, was to analyze the general chemistry portion of the Cengage OWL database. So we got data from them, which, by the way, took me 6.5 months to get. And the initial data set comprised 10 million individual responses for 90,000 students. John is one of the few people you'll ever see who can tell you that he overflowed an Excel spreadsheet on several occasions. So when he put his data in, he'd have to truncate it because he had filled every cell in a Excel spreadsheet. 64-bit or 32-bit? I'm sorry, what?
32-bit version or 64-bit?
64. Yeah. Yeah, he was using I bought him a new computer to do this because his old one was going, Now, for those of you who have worked with OWL, you know that you can do it in question mode, which is the normal way you do chemistry questions, where you say, here's a question, get it right. If you don't get it right, we'll bring it back and you get a second shot at it. And you usually say three or four shots, something like that. And there's a mastery mode as well. And our problem was, which attempt do we need to analyze out of the maybe 15 attempts that the student has had? We had one student who had 72 attempts on one question. So we took and looked at the total information curve. This is for the first attempt. And what you'll see is that we're way up here in the high level. So what we're saying is, on the first attempt, guess who tries the problem? on homework, on the first attempt, who actually tries the problem? The answer is only your very best students. On the second attempt, your average student kicks in, and by the time you get to the third attempt, you're down to the lower ability students. And if I showed you the fourth one, it's even further down, the fifth one's further down than that, sixth, and so forth, okay? So one of the things I'm going to tell you, if you're going to do online homework, the magic number of attempts is 3. If you'll do 3 attempts, you'll pretty much find out who's hanging in there with you. If you go to the fourth one, you're only telling the difference between an F and an F minus student. Who cares? Okay? And they also have mastery mode. Mastery mode is where they'll give you 2 or 3 problems, and if you get 2 out of the 3 right, then it's considered that you have mastered the question. But it is much more randomized. So when you submit your answers, it gives you a whole new set of similar but not the same questions. Everybody with me so far? And this had 66,000 students with 1,731 questions in it. First attempt looks like the same one. Second attempt, we're back in the middle. Third attempt, it's hardly moved. Fourth attempt, it's hardly moved. Fifth attempt, it's hardly moved. Sixth attempt, it's hardly moved. And it turns out that the randomization is doing this, that the students can't clue in and answer the same question over and over and over again. So fundamentally, the randomization is keeping the poorer students from finally getting it all accomplished. The other thing that John found is that there are several topics that are nationally difficult. These include Lewis acids and bases, balancing redox reactions in both acid or base, selective precipitation reaction mechanisms, strong electrolytes in aqueous solution, and solution calorimetry if you do Mosul reaction. Well, UGA students had this problem, they had this problem, and they had this problem. So it looks like those 3 are pretty much national trends. By the way, organic faculty. This is why it's so dadgum hard to teach organic. Organic is nothing but Lewis acid base, right? It's almost exclusively that. And so the students, the faculty are having, if we can't get this idea across to them, the students are going to continue to struggle. This is one we need to work on, is this concept of Lewis acids and bases. So can we show any longitudinal improvement? So what I'm going to show you now is known as a Gaussian distribution. So this is the year before we started doing IRT analysis at the University of Georgia. This is the first exam in first semester of general chemistry. And what it plots is the student abilities versus the number of students, the frequency of them. And guess what we had? We had what's known as a binodal distribution, right? So a year later, we started figuring out how to do things. And you'll see it has changed. And what's happened is our gap right here has more or less gone away. So we were taking poorer students and converting them into better students. 1 year after that, we've almost filled it in. Now, there's a way to do that, of course, and that way is to make your test easier and easier and easier, right? Yeah, we didn't take that approach. What we did was we made the test harder and harder and harder over time. So if you'll look, this is the ability you need to get an A, and it went up from 1.5 up to 1.9. Same thing for the B's, the C's, the D's. They all went up. So over time, we were making the class harder and resulting in improved results. That's kind of fun. Stop and think about it. So how do you convince the rest of the world that you're actually doing what you're doing? Well, it turns out that IRT does normalization. So it takes each year's group of students and basically it washes out any changes we get from year to year to year. But we had to do a little arithmetic here to figure this out. And if at least 15% of the test items are the same from year to year, you can take and do what's known as an IRT equating system that Lord and Stocking figured out. And so what it does is, remember this curve from before? what it does is it says, okay, let's put all of these on the same, for those 15 questions, we'll use them the same. We'll see how the other questions have varied in order for it to get that way. And it will take this curve and it'll change the slope. And then it puts everything on the same slope and says, how did you do from year to year to year? And when we did that, what we found is that we started out here, we went to there, then we went up, and we went up, and we just kept going up. So over time, our students there were improving in a longitudinal fashion, which is kind of cool. Stop and think about it. This will make deans happy. Keep them off your tail, too. Okay, so are we operating in a vacuum? Is it just us, or do we have some external measure to do that? So we went to the ACS exams. We started giving ACS exam tests at the end of every semester to see if this was a real phenomenon. So here's our first term general chemistry exam data. The average student at UGA was making a 71 percentile, and the mode is 76. It's on 1,360 students that did this. That, by the way, I've spoken with my other general chemistry colleagues. They say they can get that in their section. They've never seen any place that could do it in all sections, except for the University of Georgia when I was there. Okay? A year later, son of a gun, we're back up in the 70th percentile. So we've got our external proof that what we're doing is a real phenomenon. Okay. Any questions before I go any further?
This is worse than the previous year, isn't it?
A little bit.
How do you call it an improvement?
I didn't say, I said about the same, is what I said. That it was a 71.1 as opposed to a 70.4, so it's 0.7 of a percentile different on about the same number of students. Okay, is that fair enough? Okay, if we can hang in the 70s, we're doing okay, the way I look at it. So, at the University of Utah, UGA wouldn't let me take my testing program with me, and so I'm rebuilding my testing program. And what we're going to do there is web-based assessment across the entire state. So I have some other universities that are willing to let me basically host their tests for them. And then we're going to analyze that. And what I want to be able to do is to say, students across the state of Utah don't understand this and this and this. If we can all tackle that, maybe we can get a significant improvement for the entire state. The other thing that we're doing is that students in high schools in the state of Utah can take what's known as a technology-intensive concurrent enrollment class. And so they will also take their test on my testing system, and we will analyze that data and send it back to each individual high school teacher and say, your students understand topic A and they understand topic B. It's C that we need to work on. And it may be in a different school. It may be A and C they understand, but B that we need to work on. So we're going to see if we can pull that off as well. Come on. All right. The last thing I want to talk about is how we've changed our instruction. When I got there, we were lucky if we had 50% attendance. The students have pretty much blown off the classes. And so we're having a heck of a time getting them to show up. And we had a lot of other issues. So I decided to do something radical. So I went to what is known as a flipped classroom model. And we've done this. I'm now in the second year of this. Now, the way a flipped classroom model works is the students are required to do homework and they're reading before they come to class. And then in class, we assess how they have done on their homework and reading. We do it using clickers. And I've set it up so that 20% of their grade is homework, 20% of their grade is in-class clicker responses. And so now not too surprisingly, our attendance is about 90%. And we've tried a few other tricks here. I will warn you that this is not for untenured faculty. Neither is it for faculty who are wimps or departments that have weak need chairs or deans. And the reason is that the students are going to come tell you, you're not teaching. To which I reply, you're correct. I'm not, but you are learning. And that's more important. Okay? So you got to have some backing in order to do this. But what we did was gave the ACS final exam before I started doing this, and we had 3 sections, and here are their percentages. And then 1 year later, in the flipped classroom model, here are the sections. And you can see that we've got an improvement of from 60% up to 72% and so forth. So we increased our overall average significantly. All right, last couple of things here. Come on, clicker. All right, so what I hope I've told you is that item response theory is a very effective way for you to assess how students are doing. We've implemented a few interventions that we can show helped our students improve, and we have performed an IRT assessment of our national homework system. So let me finish up here. I need to thank my former department chairs at UGA who allowed me to do a lot of this stuff, make more mistakes than most people should be allowed to make, and they didn't fire me at any point in that process. I also need to thank Henry White and Cindy Burrows, who are the department heads at Utah, who are allowing me to make some of the same mistakes for the 3rd or 4th time, as well as Ron and Eileen Lagsdale, who endowed the chair that I have. And a lot of this work was done on a PRISM project from the NSF. And I thank you for your attention. Yeah, Rick?
Yeah, in your flipped classroom model, your slide said that your class consists of iClicker questions. What fraction of your class time is the iClicker question?
100%, if possible.
100%. Okay, so it's very flipped. I understand. I was wondering if you really meant that.
What I do is if I get 90% of them getting the question right, I don't spend any time on it at all. If I get 60%, then we stop and I start showing them how to do something. So I'm trying to figure out where they don't understand stuff and put my time in on that. Okay, did I answer your question?
Yeah.
So when you have to stop, are you using peer instruction, or you try and get students to...
Me and 300 students. Me and 350 students.
No, peer instruction is the term meaning that you actually challenge students.
Oh, okay, now I understand. I'm sorry.
They become the teacher and the learner.
I'm sorry, I misunderstood your question. Yeah, when I put a question up there, they are allowed to help each other.
Okay.
Yeah, so we do have a lot of classroom interaction where they're talking to one another.
I'm impressed because, in essence, you mentioned most of the topics that I have identified personally as being challenging when I teach general chemistry, and I've been doing this for quite a while. Certainly nomenclature seems to be something where I wish I could use a baseball bat for obvious reasons that is not allowed as a technique. But my question is, do you achieve good results by asking them to memorize the structures? Do you use the VSCPR theory or simple Lewis dot structure? In other words, what is the method that you used when you said that they were forced to draw structures? Was it simple memorization?
Oh, okay, now I understand.
Was there a little bit more chemistry behind it?
I didn't actually, the drawing of structures, we're using the same words but different terms. Okay. So if I asked them to draw the structure of this, what I was hoping they would do is draw that and 3 of these. Okay? And that's what I'm looking for. Can they recognize that the hydroxide units, I misdrew the hydroxide, didn't I? Yeah. Can they recognize that it's the OH groups are subunits? And that's what I'm trying to find out.
Wouldn't that work the same way if there were brainwash from the get-go about Lewis structure? where it's a little bit more complicated. It's not as simple as you presented it.
If you can get them to make this leap of faith, Lewis dot structures become much simpler. And one of the tricks I have done is to have them do a reaction. So I'll tell them, let's take silver nitrate and react that with sodium chloride. And we're going to form silver chloride and sodium nitrate. Whoops, I'm screwing this up left and right here. And I give them the states for it so they know everything. And I say, draw this one. I want you to have 6 formula units of this, 6 formula units of that, and draw what it looks like when we're finished. And I'll do that and then walk around and look and see. Now, it turns out that if you do that, you're lucky if 1% of them will get it right. And the thing they screw up mostly is forming a solid state with silver chloride. So you'll have silver chlorides clumped together, but there'll be one here and one over there and one here, and they're not, doing them. So then I take and I call up a movie I have on here of a molecular representation of that reaction. I say, watch this movie, don't say a word. And I run the movie the whole way through, and then I come back and say, okay, I'm going to stop this movie at various points. I want you to tell me what they are. And when you do that, it takes that and it converts it to something that they can understand. And they at that point, they start nailing them. Oh, okay, I got that. Now I figured out. And they can hit every one of those. And I found that to be a very effective way to get them to understand what these symbols mean to you and me.
The only item that was not in your list, and I'm really frustrated by it when I teach it, because I'm supposed to be a kineticist by profession, is chemical kinetics. So it seems that they don't, if I make any question that is a little bit more challenging, forget it. They're not going to get it. Now, you seem to have a different experience with it?
Our students could knock out just the simple first order rate laws and stuff like that. Mechanisms they had trouble with. Yeah. Yeah.
I was just wondering, when you guys use the ACS exams to validate your findings, did those two groups take the same version of the ACS test? And I only asked
yes.
I took 2 different versions of the analytical ACS test, and the first one I took, I got a 94 percentile, and the second one I took, I got a 74 percentile.
These were the exact same tests.
Same test.
The only thing was we threw out the ones that students had written on and bought new ones at some significant cost, I might add.
At Georgia, it seems like this was done department-wide for all the general chemistry classes. How much is there a problem with getting professors to jump on board?
Yes.
That's what I thought the answer.
Yes. But what you have to do is show that things are getting better. And then after they come to realize that the results are working, then they're on board. And the other thing that I worked hard at was to make the transition painful for me and not painful at all for them.
So the testing for that first part of your class, you're collecting all the results and analyzing them. How do you get the results? Would you transcribe from the handwritten tests into a spreadsheet or something?
No, the computer takes care of all that.
How does it? Is there a computer at each desk in the lecture hall where the students are taking?
Oh, we have a testing center. So we put them all in this case, at UGA, it was a 40 computer room. And we'd run 2,200 students through there in a week. At Utah, I have 108 computers in one room, and I can do my entire class in 2 days.
So the students move through in shifts throughout several days?
Yeah. We give them a schedule and say, here's a time, here's a time, here's a time, and you can go in and choose a time that will match with your schedule.
How do you prevent students from telling each other what their questions on the test?
I randomize it to the point that it doesn't matter. So one of the cool things about this is every group that sits down has a unique test. But the cool thing about IRT is I can show you that this question and that question have the same difficulty. Therefore, I can build a test that has equivalent difficulty from one test to the next test to the next test. And it randomizes things such as your question number 1 is my question number 5. If it's a multiple choice question, your correct answer number A is my correct answer D, and so forth and so on. So every group has a unique test. And what we do is, for instance, we're going to do a gas law question. We'll put, let's say, 4 gas law questions in there, and the computer will pick this one for the first group, this one for the second group, that one for the third group, that one for the fourth group. And it's doing the same thing for the other questions. So it's making a unique test for each session. Did I answer your question?
I have a question. One of the slides you showed, you said that it was sort of a snapshot of the time, where you had sort of topics that were either very difficult or
very easy.
Now, the question I have about that is, presumably, and you can correct me if I'm wrong, the first, let's say, maybe 3 quarters may represent 3 exams, right? I don't know how many exams you give, but I'm saying, let's
3 and a final.
3 and a final, okay, perfect. So, the final is probably the only test that's cumulative.
Correct.
Right. So what I don't understand, if we're looking over that snapshot, you may have sort of a huge peak on exam 1, which in the final would sort of disappear, meaning that they learned it. But there were some things that were like bigger than anything else, which means that maybe they understood it in exam 2, but now they don't understand it in the final. So that's what sort of confused me about that.
Yeah, we did not do that analysis, but we should have. It's a good idea.
I was wondering, you showed improvement over years, but how would you use this item response system to improve the performance within the same semester? Is there a way?
Oh, well, unfortunately, you have to collect the data first. But then once you've got the data collected, then you can go back and say, okay, we need to work on this next year.
So it's not for the same students?
Not the same students. But what we did was that way. There's no way for us to tell, because after we take the data, the test has already been given fundamentally. Okay?
There's no way around.
Is there a way for you to do a chemistry experiment and say, I know I'm going to get this result? It's the same thing. I mean, we're doing an experiment.
Well, there's some similar way we do for collecting data, like we ask students what is the hardest point for you at the end of this lecture. And we'll come next lecture and probably try to target these items.
Yes, you can do that. And there you're not so data-driven as you are, they're feeling-driven. So do they or do they not? Mine is much harder in terms of the actual data that you're collecting.
But they're not benefiting from it.
The first group did not. The second groups, the third groups, the fourth groups did. There's another question over here. Yes?
Do you measure how the students do on related topics in the subsequent
classes? Yeah. We saw an immediate 10% improvement on their first test in organic, and we also saw a significant increase in the number of students who got into organic and stuck it out. Did we go back and look at the actual individual topics? And the answer is no.
I was just wondering because when you did the example, you used the weak acids versus strong acids, then I didn't see the topics in Gen Chem 2 that you used, and I was just thinking, how did they do on, for instance, calculating the pH of a weak acid?
Oh, okay, yeah. We've done similar analysis for second semester in Gen Chem, yes. So we have done that, and we can see that there is if we get them to understand that stuff in first semester, they do better in second semester. But I thought you were asking me, do they do better in organic, and I don't have that data. I'm sorry, I misunderstood your question. Yes?
So you alluded to this early on in your talk, and I'll just say I'm from the physics department. So I'm just curious to hear about how the IRT analysis has been implemented in other fields, and if you understand there have been differences and different.
It started out in
the teaching strategy, but the analysis that's come back.
Yeah. It started out in psychology, so it's been used there. But I'll tell you, every student you see at this university has been assessed using IRT. It's called the ACT and the SAT. That's how they do it. They basically, they're fantastic IRT folks. And this new model they're doing, this adaptive testing, which you may have heard of, where you answer the first question and then it gives you a different question depending on whether you get it right or wrong. That's IRT up one side and down. What they do is they hit you with a 0 ability question. And if you answer that right, then they'll go up to a 0.5 question. If you answer that right, they'll go to a 1 question. They keep going until you start missing it. And at that point, they figured out your ability. Or if you miss the first one, they'll drop down to -0.5, -1, so forth and so on. So this is how ETS makes their living.
Okay. But are you aware of it being implemented in other specific fields besides like?
No. I'm still trying to get it implemented in chemistry. Unsuccessfully, too, I might add.
This is really good for the content side of education, but at least to me personally, education also includes creative processes and finding what you're motivated about. How do you go about measuring those other aspects? Creativity or critical thinking? And do you see with your flipped classroom improvements?
Yeah, the answer to that is I don't know of a way to do that well, although people are working on that. What we do is we try, we've made some changes in our labs, and so what we do is we teach techniques. So we teach a technique the first week, a technique the second week, a technique the third week. Then the fourth week, we basically say, there's something in this bottle, tell me what it is. And in order for them to figure it out, they've got to take the other ones and put them all together. And we make them, we tell them what that problem is going to be. They have to go off and write a procedure proposal. Here's how I should do this experiment. We grade that, give it back to them. They come in, they do the experiment, and then we make them write a formal lab report. And so that's the way I've attempted to tackle that. Did I answer your question?
Yeah.
Yes?
Back to the ability part of your graph, how is that actually measured? Is that is it objectively or is it subjective?
The ability part is normalized to the students.
Right. So
if you made 100 on the test, right, we're going to say that you've got an ability of, let's say, a 3. Right. If you make a 75 on the test, we're going to give you an ability of 0. But it's going to be something along that lines. By the way, I don't know if it's your ability. I have no idea who these students are on an individual basis. Okay.
And is that how you normalize like a question? Like, for instance, how did you say that that the aluminum nitrate and how many ions is an ability of 0.33? How were you able to get that ability value? I guess
the Bilog MG3 program calculates all that and spits those numbers out for us. Okay, so it does this iterative process, and I'm glossing over a lot of the details of how that's actually done. So it turns out it's a relatively sophisticated integration of stuff that we're doing. Did I answer your question?
Well, if there are any more questions, I welcome you to come on down and talk with Dr. Atwood. Otherwise,